Welcome to Network Basics Module 1, Understanding IP Addressing. In this module, we'll cover bits and bytes, basic binary math, understanding IP classes, and understanding private IP addresses. Prior to learning about IP addressing, we must have a fundamental understanding of binary numbering and binary to decimal conversion. The binary numeral system, or base 2 numbering system, represents numerical values using two symbols, either a 0 or a 1. Now let's bring this together with two terms that you're probably already familiar with, a bit and a byte. A bit is the amount of information that can be stored by a digital device such as a register and can normally exist in only two distinct states, either on or off. When we're looking at a bit, it can either be a 1 or a 0. A byte is 8 bits in any combination of 1s and 0s, and 8 bits is also referred to as an octet. Bits and bytes are in binary format. This relates to IP addressing because we use 8 binary bits to define a decimal number. To convert a binary octet to a decimal number, we have to first look at the fact that each bit position has a decimal value assigned to it. These bits are weighted from right to left in an increment that doubles in value. So if we look at this, we see that the first bit position is valued at a 1. The next one is valued at a 2, 4, 8, 16, 32, 64, and 128. Now if a bit is turned on, it actively assumes the value of its placeholder. Here we see an octet where only the 16-bit, the 4-bit, and the 1-bit are actively turned on. If we take and we add these decimal numbers together, you'll see that we have a decimal number of 21. Let's do a short self-test to see how we're doing so far. Go ahead and hit the pause button and work through these few binary to decimal conversion problems. How did we do? Did you come up with the following answers? If not, you may want to try a few practice problems on your own. What is an IP address? An IP address is a numerical label that is assigned to computers or devices, also known as hosts, participating in a computer network. An IP address in its native format is a 32-bit binary number. We divide that 32-bit binary number into 4 octets, and those octets can be converted to decimal. And the format that you're probably most familiar with, as seen in the bottom example, is known as dotted decimal notation. IP address structure. An IP address is made up of two parts. The first part is a network identifier. Starting from the left and working our way right, there's a certain number of bits that identify the network where the host or other network interfaces are located. The second portion is known as the host ID, or the host identifier. The remainder of the bits can be used to identify different hosts on a network. Address structure becomes relevant when we start talking about classful IP addresses. The first class we want to talk about is an A-class address. A-class addresses are primarily used for large networks. A-class addresses only use the first octet to define the actual network address. The next 3 octets are used for hosts. There's a total of 126 valid networks within an A-class address range. This is due to the fact that the most significant bit in the first octet, the bit on the far left, is always 0. B-class addresses are used for medium-sized networks. A B-class address uses its first 2 octets to identify its network and the last 2 for hosts. There are about 16,000 B-class networks, each with about 65,000 addresses. When dealing with B-class addresses, the most significant bit to the far left is always turned on, but the second most significant bit is always turned off. This gives us a valid range in the first octet of 128 to 191. C-class addresses are designed for small networks. The C-class address range uses the first 3 octets to identify its networks and only the last octet for host addresses. This means you can only have 254 valid host address on one C-class network. The rule is more networks but less hosts. The first step in identifying a classful IP address is a trick called the first octet rule. You can identify what class an IP address is in and what host might be in its network by looking at just the first octet. When dealing with an A-class address, the first octet is 1 to 126. A B class address runs from 128 to 191. A C class address runs from 192 to 223 in the first octet. And a D class address, which is reserved for multicasting, runs from 224 to 239. The 127 IP address range is reserved for loopback and testing purposes. I'll teach you how to use this in a later module when we discuss the ping command. Private addressing. Private IP addressing was originally defined in an effort to delay the exhaustion of IP version 4 addresses. This is also a standard in IP version 6. These are non-routable addresses. These address ranges are commonly used for home, home office, and enterprise LANs, where global routing is not mandatory. Private addresses can also be identified by the first octet. An A-class private address range is 10.x.x.x. A B-class private address range is 172.16 to 172.32. And a private C-class address range is 192.168.x.x. Let's see how we're doing so far. Go ahead and hit the pause button and see if you can tell which class these IP addresses belong to and if they are routable or non-routable. How did we do? If you got them all right, great job. If not, you need to do a couple of practice questions on your own. Now let's talk about subnets and subnet masks. What is a subnet? A subnet is a portion of the network's computers and network devices that have a common designated IP routing prefix. A subnet mask defines a separation of the network portion of the address and the host portion of the address. Here, we see a private non-routable Class C address, 192.168.5.10. As you see, the subnet mask is 255.255.255.0. Looking at this, we can see the true separation between the network portion of the address and the host portion. 192.168.5 is the network, and the .10 is the host address. Taking this same example and putting it in a real-world application, we see that all the machines pictured here belong to the same network or subnetwork. They all belong to the 192.168.5 network. Their host address only take up the last octet, because remember, in a C-class address, the octets are network, 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 host. All devices, when working with IP addresses, have a default subnet mask if no true subnetting has been done. The default subnet mask corresponds with the octet layout of the class address that you've assigned to the device. Notice here, a default subnet mask for a Class A address is 255.0.0.0. Working with an A-class address, the octet layout is network.host.host.host. Thus, the mask separates the network portion of the IP address from the host portion of the IP address. This brings us to the act of subnetting. Subnetting is the act of borrowing bits from the host portion of the address and giving them to the network portion of the address. This creates smaller, more manageable networks and also increases security. You've actually already learned how to work the numbers on this chart. The only thing we're doing now is we're working them backwards. If we look at the bottom of the chart and we borrow one bit from the host portion and give it to the network, we have a 128 subnet. If we borrow 2 bits, we now have a .192 network. 3 bits is 224, 240, 248, 252, 254, and 255. The more bits we borrow, the more subnets we can create. But you'll notice by the chart, we lose the number of hosts that we can have on each one of those networks. Here's a very simple example. We're going to take a Class C address and we're going to borrow 2 bits from the host portion of the address. That will create a .192 subnet. By doing this, we can create up to 4 subnets. We have a 0 subnet, a .64 subnet, a .128 subnet, and a .192 subnet, depending on how we flip our bits on and off. In this very simple example, we want to look at the effects of subnetting. Here, I've created a .64 subnet. Within that subnet, I have a valid host range from .65 to .126. .127 is not a valid host address. It's a broadcast address. It's all ones. So the last valid host address I have in the .64 network is .126. We basically just created a network or a subnetwork that can only contain 62 valid host addresses. This makes a smaller, more manageable, and more secure network. In our next module, we'll be covering network topologies and cabling. Thank you.